Hello again. This is 2233 coming to you from the College of DuPage. The title of this lecture is Tangential and Normal Components of Acceleration, and as always, please be an active learner. When we study the motion of particles, it's often useful to resolve the acceleration into two components, one in the direction of the tangent and the other in the direction of the normal. These are perpendicular, and we've done this before, resolving things into components. If we write v equal the magnitude of the vector v for the speed of v, then we know the unit tangent vector t of t is r prime of t over the magnitude of r prime of t. And that's going to be v of t over v of t, magnitude of v of t, which is this v here, and that's the vector. So it's 1 over v times the vector v. If I multiply both sides of this equation by this v, which is a scalar, I get that v, the vector, is equal to the scalar function v times t. So if we differentiate both sides of this equation with respect to t, this is a product rule. So we will do the rule. So what we get is the derivative of the first times the second plus the first times the derivative of the second. Now, we do know that the curvature is the magnitude of t prime over the magnitude of r prime, which the magnitude of r prime is v. So we have this. So we know that the magnitude of t prime is the curvature times v. And so what we're going to do is we're going to substitute for t prime up here. And so t prime is going to be n times the magnitude of t prime, and we're going to substitute this in. You want to check this algebra, but this is what you get. So a then is equal to, in the tangent direction, it was v prime t, but in the other direction, it's going to be kappa, the curvature, times v, the scalar function squared, times the normal vector, the unit normal vector. And you see now we resolve this into components in those two directions. And so this is a sub t, this is a sub n, and we have, by identifying the components, that these are the components in those directions. Now that's a good formula, but it's often, and here's the picture of what it is. Here's the acceleration vector for this particular curve. It's curving this way, so it's into the inside of the curve. So this is the magnitude of the tangent, that's the magnitude of the normal. And here was the expression we derived. So this is useful, and we will be using this. Let's look at what this says, though. The first thing you notice is the binomial vector is not here. So no matter how an object moves through space, its acceleration always lies in the plane of t and n, the oscillating plane. And recall that t gives the direction of motion, and n points in the direction the curve is turning. And next we note that the tangential component of the acceleration is v prime. That makes sense because it's the derivative of how fast it's going. But the normal component is moving towards the center, and that is the curvature times v squared. This makes sense because if you're turning a sharp curve in the road where you have a large curvature, the acceleration will throw a person against the door of the car. And also, if you do a high speed there, it will do it even more because you see that's being squared there, and so it's increased by a factor of 4. Now, although we do have a nice expression here, it turns out often it's more convenient to have these coefficients depending, the scalar function coefficients, depending on r, r prime, and r double prime. So to this end, we take this equation from before, and we're going to dot it with a. So we're taking this equation dotted with the equation for a that we had before. We're going to distribute, and we're going to note that t dot t is 1 and t dot n is 0. So this is just v times v prime. This is the scalar function. And so that means that if I were to divide both sides by v, I would have that v prime is equal to v dot a over v. And writing that in terms of r double prime and the magnitudes gives me this equation, a useful equation for the tangential component. Similarly, we have an expression for the curvature, and it's this expression right here that we derived earlier. And so if we put that in here, then we have this expression. But notice that we have r prime magnitude squared and r prime magnitude cubed. So some of those cancel out, and we're left with this expression. Please make note of this equation, and this is one that we will use frequently. And let's use it right now. Here's a problem. A particle moves with position t squared, t cubed. Those are pointing brackets. Find the tangential and normal components of the acceleration. You know what to do. Let's see how you did. Okay, so here we're taking the derivative in the first and second derivative and taking the magnitude. You should verify these calculations. So then for the a sub t, we use this equation. So we're taking the dot product of this one with this one, and simplifying, we get this. And I'm dividing by the magnitude of r prime, which is this. So that is a sub t. Now, to calculate a sub n, we have to take the cross product. So I take the cross product of r prime, which was up here, and r double prime, and I use my matrix notation or determinant notation for that. I do the calculation. Again, you should verify this, but we get 6t squared in the I direction minus 6t squared in the j direction. Okay, so then this is the formula. This is the numerator divided by the denominator, which is the same as the denominator up here. And I simplify this. When I dot this with itself, I get this, and then I take the magnitude, so I take the square root of that. Actually, I'm taking the cross product. I do this calculation here, but then when I take the magnitude, I'm going to have 36 t to the fourth, and here I'm going to have another 36 t to the fourth, and when I simplify it, I get this, and that is the normal component. Sometimes to calculate a sub n, we could use this formula, that a sub n is equal to the square root of the magnitude of a squared minus the magnitude squared of a sub t, just that number squared. And that formula comes from this. If we take the magnitude of a squared, we learned in our first chapter on vectors, that's a dot a. So this is going to be the square of the components. And I solve this for a sub n, so I subtract this from both sides and take the square root, and here is that formula for calculating the normal component of acceleration. And it can be simpler doing it this way because we don't have to calculate the curvature. So here's an example. So without finding t and n first at all, look at this for r of t and put it in the form of where we have a is equal to at times t plus an times n. And you can do this without finding t and n. You know what to do. Let's see how you did. Okay, so here's the calculation. So this was our r, and so we're going to take the derivative to find dr dt. Now notice that you got products, so there are product rules that are happening here. And also notice when you do the algebra that things cancel out. These cosines will cancel out and these sines will cancel out. So this is what you're left with as dr dt. So the magnitude is going to be the sum of the squares, and we'll note that cosine squared t plus sine squared t is 1. So this ends up just being, I factor the square root of, I factor t squared out of there, so it's the square root of t squared, absolute value of t. T is greater than 0, so this is just t. But now I'm going to take the derivative of that to get the tangential component of the acceleration. This is the formula we have for that, and so that is going to be 1. Now, since we know a sub t, we can use the equation that we had, and we'll know that a sub n is the magnitude of a squared minus a sub t squared. And again, when I take the magnitude of this, I'll use the fact that sine squared and cosine squared, sine squared t plus cosine squared t is 1. I can simplify it to get this. So I'm going to have t squared plus 1 minus 1, and I get t. So the answer to this problem is t plus the unit vector, capital T, plus t, the scalar function, times the normal vector. And by the way, this equation here is known as the invalid of the circle, and it's the same thing as if you had a string around here and you're pulling the string off, but keeping it within that plane. That's the equation that you would get. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.